Section 3.7 is going to walk us through a process called implicit differentiation, which is what we do when we're trying to find the derivative of a function that has not been clearly defined for us. It's actually quite a tricky little process that's going to use a lot of algebra and chain rule. Okay, so we're going to begin. Let me just tell you again when we use implicit differentiation. And hopefully the word implicit will be a clue as to like what kind of context you would use this in. So this is the way you find a derivative for a function that has not been explicitly defined. In other words, we don't even know what the function is. We just know that it's a function of x. So we are not told what the function is, but it is implied or implicit that it is a function of x. And so because of that, it's going to require a lot of a chain rule. So for this process, we will need to use chain rule. And that is why this section could not come until after section 3.6, which was on the chain rule. So what the process is, first you're going to differentiate both sides of the equation with respect to x. When you do that, what you need to look out for is the product rule and the chain rule. And not only that, but when you would use one over the other. So keep your eye out for that, which I'm going to help you do. The second thing you would do is you would collect all the terms with dy dx in them, which will make sense as I go through the first example. And you want to collect them onto one side of the equation. The third thing you're going to do, if necessary, so this one you don't always have to do it, but if necessary, you're going to factor out the dy dx from all of its common terms. And then the fourth step is you're going to solve for dy dx. Now, of course, this was our goal all along. And if I knew what y was as a function of x, I would simply just take the derivative using our other rules. But this is what I use to find the derivative of y with respect to x when I don't even know what the function y is. Also, these two steps right here, all they are intending to do is just isolate the dy dx so that we can solve for dy dx. That's really our only goal here. So let's do that process with example 1. In example 1, I have the equation x to the third plus y to the third is equal to 18x times y. The reason why this is considered to be implicit is because it's not written in the form y equals blah 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 x, right? It's not, we're not told what y is as a function of x. In fact, we don't even know what y equals. But we're being asked to find the derivative of y with respect to x. So what we're going to have to do is be very creative. We're going to go term by term and take the derivative of each term separately, and then we're going to collect all the terms that have a dy dx in them. So you're probably wondering where the dy dx is going to come from. It's going to come from when I have to use the chain rule. So let's go through each term and see which rule I would have to use. Well, this first term here is what I would refer to as explicit because it's telling me what the function is. It's x to the third power. So all I'm going to have to do there is use power rule, no big deal. That's the easy part. This part here, the y to the third, that's what I would call implicit because I don't know what y is. I know it's a function of x, but I don't know what that function of x is. So I know that what I have here is some function of x, which I don't know, being risen to the third power. So this is actually going to require chain rule plus power rule. Because I do have a power function. I have a function of x to the third power. But I'm also going to have to find the derivative of that function of x. Okay, and then over here with the 18xy, what I have right there is actually a product. I've got an explicit function, which would be the 18x part, because it's just 18 times x. That's explicit. That's what the function is. But then I also have this y. So I have a product of an explicit function, 18x, times an implicit function, which is y. And remember, I don't know what y is. I just know that y is some function of x. And what that function is, we don't know. So in this scenario here, because it's an explicit function times an implicit function, we're going to actually have to use the product rule. So that's what the last piece requires. So let's go through term by term and find dy dx. So for the first term, it's just a function of x to, or it's just x to the third power. So I just use the power rule, and I get 3x squared. That's the derivative of x to the third. Then for the derivative of y to the third, I'll begin with the power rule because that's the outside layer. So I'll begin with 3y squared. But then I have to multiply by the derivative of the function of x. Well, that's just the thing. I don't know what the function of x is. So what we're going to do is we're just going to call that derivative of y with respect to x, we're just going to call it dy dx. So it's 3 times the function of x squared times the derivative of the function of x, which we'll just call it dy dx. So that was the chain rule right there. Meanwhile, on the right side, I have to use product rule, so let me do that work over here. So u in this scenario would be 18x. V in this scenario would be y. U prime would simply be 18 because it's just the constant in front of x. And then v prime, again, I don't know what y is in terms of x. So I can't use a rule to find the derivative of y. I just give it a name. Derivative of y with respect to x. That's the derivative of y. So it's kind of like saying, what's the derivative of y? Oh, it's the derivative of y. Okay, so then I'll do u prime v, which is 18y, plus v prime u, which is 18x times dy dx. So basically what we've done is completed step 1. We've differentiated both sides of the equation with respect to x. Okay? Now what I need to do is collect all the terms with dy dx in them onto one side of the equation. So this, I'll just go ahead and move this term over here. So I have 3y squared dy dx minus 18x dy dx equals, and then I'll leave this term where it is, 18y, and then I'll subtract the 3x squared over to the other side, so minus 3x squared. And then let me bring my work up and over here. So then what I'm going to do is factor out the dy dx in order to isolate it. So I have dy dx times 3y squared, because that was what was left over from that term, minus 18x, which is what's left over from the second term. And all of that is equal to this stuff here that was on the other side, the 18y minus 3x squared. So then I have to solve for dy dx, and so in order to do that, I'll just divide both sides by the 3y squared minus 18x. And then I'm left with dy dx equals this quotient here, 18y minus 3x squared divided by 3y squared minus 18x. And then if you can simplify, then you have to simplify. And I notice I can factor out a 3 from the numerator, and I can factor out a 3 from the denominator and then cancel. And so my final answer would be 6y minus x squared all over y squared minus 6x. And that's my final answer. I want you to notice also that in my answer for dy dx, I have y in there. Notice my answer is not just in terms of x either, and that's okay. When you're finding a derivative implicitly, you might have some y's left over in your answer, and that's okay. What I'd like you guys to do right now is pause your video and attempt this U-try. Come back and see if you got it correct. Okay, so what you should have done for the U-try is take the derivative of x, which is just 1, and then take the derivative of sine y with respect to x, which means you're going to be doing chain rule. So you would take the derivative of sine, which is cosine, of the block, which is y, times the derivative of the block, which is just dy dx. Then we want to isolate dy dx. So to do that, we would just divide both sides by cosine y. So I have 1 over cosine y equals dy dx, and then I want to just simplify my answer. And so 1 over cosine of anything is just secant of that thing. So 1 over cosine y is secant y, and so that's our derivative of y with respect to x. Okay, moving along to the second example, which is asking me to find the lines that are tangent and normal to this curve. So this is the equation of a curve that contains both an x and y variable, but it doesn't have y solved in terms of x. So again, I need to use implicit differentiation. So first thing I want to remind you guys is that once we find dy dx and then evaluate that at the point rad 3 comma 2, that would equal the slope of the tangent line to the curve. So once I find the derivative, evaluate it at the point, that's going to give me the slope of the tangent line. And then the point given to me here, the rad 3 comma 2, that's a point on the tangent line. Then once I have those two things, I can use point slope form, which is the process for finding the equation of a tangent line. So I'm going to block off some space here, and we're going to work over here to find dy dx. Okay, so first thing I notice is this first term here again is explicit because it's just telling me that the function is x squared. So for that I would use power rule, 2x. For the second part, that's actually a product rule because I have a product of an explicit function, negative rad 3x, times an implicit function y. Again, y is some function of x, but we don't know what that function is. So maybe I'll do that work up here. So u would be the negative rad 3x. V would just be y. U prime would just be the constant in front of x, which is negative rad 3. And then v prime, again, since I don't know what y is, and I'm trying to take the derivative of y with respect to x, I'll just call it derivative of y with respect to x. So the derivative is just the name for the derivative. And then we'll do u prime v plus v prime u. So u prime v would be negative rad 3y plus v prime u, which is negative rad 3x times dy dx. Okay, then this third piece here is a function of y. And y is a function of x. So it's a function of x. So this third piece will require the chain rule. So first I'll just take the power rule. I'll do the derivative of the outside, which would be 4 times y. But remember, y is a function of x, so that I'm going to multiply that by the derivative of the block. And in this case, the block is y. So the derivative of y with respect to x is simply dy dx. Then coming over here to 5, it's just a constant, so the derivative of that is 0. Now I'm going to go ahead and collect the terms with dy dx together, and I'm going to move everything else to the other side. So I have negative rad 3x dy dx plus 4y dy dx equals, and then I need to add the rad 3y to the other side and subtract the 2x to the other side. So I'd have positive rad 3y minus 2x. Okay, now I'm going to factor out the dy dx. and that leaves me with negative rad 3x plus 4y equals rad 3y minus 2x. Then I'm going to solve for dy dx by dividing this term, the negative rad 3x plus 4y, to both sides. So my dy dx is going to be rad 3y minus 2x all over negative rad 3x plus 4y. And I'm going to evaluate that at this point, rad 3 comma 2, because that's I need to know what the slope of the tangent line is at that point. This is telling me what the slope of the tangent line would be at any point x, y, but I need to know specifically what it would be when x is rad 3 and y is 2. So wherever there's an x, I'm going to plug in the rad 3, and then wherever there's a y, I'm going to plug in the 2. So I have rad 3 times 2 minus 2 times rad 3 all over negative rad 3 times rad 3 plus 4 times 2. So that's going to equal 2 rad 3 minus 2 rad 3 all over negative 3 plus 8, which is equal to 0 over 5, which is equal to 0. So after all that work, the slope of my tangent line is equal to 0. So that's what I have right here. So it equaled 0. So now I'm going to go ahead and do my equation. For part A, I'm doing the equation of the tangent line, so I would just use this dy dx slope that I just found. So I'd have y minus 2 equals 0 times x minus rad 3. Well, this 0 is going to wipe out this whole expression, because 0 times anything is just 0. So I'll end up with y equals 2 for my answer to part A. Then for my answer to part B, I'm supposed to find the equation of the normal line. And if you recall, the normal line is perpendicular to the tangent line. So that means that the slope is going to be the negative reciprocal. Well, the only issue is when you take the reciprocal of 0, you end up with infinity, or you end up with something that's undefined. So basically it's a vertical line going straight up and down. So the only equation that I could have is x has to equal rad 3, because it has to be going through this point, and it has to be vertical, meaning it's going straight up and down, and it has to pass through the x-axis at rad 3. So the answer can be x equals rad 3. Alright, so here I'd like you to stop the video and try a similar problem and check your answers when you're done. Okay, for the you try, first when you're taking the derivative of everything, you should have used power rule for the first one, 2x, plus power rule and chain rule for the second one, 2y dy dx, and then derivative of 25 is 0. Then after doing some algebra, we should be able to find that dy dx is equal to negative 2x divided by 2y, which reduces down to negative x over y. But that's my slope at every point x, y. I want to find my slope specifically when x is 3 and y is negative 4. So I'd plug in 3 where the x is, negative 4 where the y is, and that reduces to positive 3/4. So then my answer for part A, I just simply plug the point and the slope I found into the point slope equation. So you get y plus 4 equals 3/4 times x minus 3. For part B, you use the exact same point, but you just take your slope for the tangent line and you flip it and make it negative, because remember, the tangent line and the normal line are perpendicular, and perpendicular slopes are opposite reciprocals of each other. But it's the same point, so you still have y plus 4 equals negative 4/3 times x minus 3. And now for our last example, and possibly the most difficult. So make sure that you walk through this slowly as I go through it, and pause the video as needed to make sure you're following along. Okay, so for the first part, I'm going to do the first part kind of over here. First, we're going to find dy dx by using the same process we've been using. So for x to the 2/3, I would use the power rule, and I would have 2/3 times x to the negative 1/3. For the y to the 2/3, I would still use power rule because it's y to the 2/3, but I would also use chain rule, because remember, y is a function of x, so it's a function of x to the 2/3. So I would do 2/3 y to the negative 1/3 times the derivative of y with respect to x. And then the derivative of 1 is just 0. So then I'm going to rewrite this just to make it a little easier to see what's in the numerator versus what's in the denominator. So I just sort of rewrote what I had. I'm going to subtract the 2 over 3x to the 1/3 and bring that to the other side. So I have 2 over 3y to the 1/3 dy dx equals negative 2 over 3x to the 1/3. So then I'm going to multiply both sides by the reciprocal. Let me give myself a little bit more room here. So I'm going to multiply this side by 3y to the 1/3 over 2, and then same thing to the other side. So I can solve for dy dx. I can get dy dx alone. Well, the 2's will cross cancel and the 3's will cross cancel, and I'll have negative y to the 1/3 divided by x to the 1/3. And that is my dy dx. So I've finished the first part of this problem. Now for the second part. The second part is asking me to find the second derivative of y with respect to x. So I'm actually going to begin with my first derivative. So let me write that over here. And if you notice, it's a quotient. So I'm going to have to use quotient rule. So I'm going to let u equal negative y to the 1/3. V will equal x to the 1/3. U prime, well, I'll just use power rule and chain rule. So it's negative 1/3 y to the negative 2/3, because I have to subtract 1 from the power. But this is y to the 1/3, so it's a function of x to the 1/3. And so I have to multiply this by the derivative of y with respect to x. Well, we know that the derivative of y with respect to x is equal to negative y to the 1/3 over x to the 1/3. So I need to substitute that in and find my answer using that. So I have negative 1 over 3y to the 2/3, because that exponent was negative, so it should go down to the denominator. And I'm going to multiply that by negative y to the 1/3 over x to the 1/3. Well, I notice my negatives are going to cancel, and one of my powers of y is going to cancel. So I'm going to end up with positive 1 over 3 y to the 1/3 x to the 1/3. That's my u prime. And then v prime is the derivative of x to the 1/3, which would just be 1/3 x to the negative 2/3. And if I simplify, that's 1 over 3x to the 2/3. Okay, so now I'm going to do u prime. I'm going to use this for u prime. U prime v minus v prime u all over v squared. So d2y over dx squared is equal to u prime v. So that's, let me write it down here, 1 over 3y to the 1/3 x to the 1/3. That's u prime v, which is x to the 1/3. And we'll just put that over 1 just to keep clear what's on the top versus what's on the bottom. Minus v prime u. So v prime is 1 over 3x to the 2/3 times u, which is negative y to the 1/3 over 1. All of that is being divided by v squared. So that's x to the 1/3 squared. So now we're going to go and do some simplifying. I notice that in this first part, the u prime v, that x to the 1/3 is going to cancel out. And I think that's the only thing that simplifies. So I have 1 over 3y to the 1/3. And then I also notice that this subtraction cancels with that negative, so I have plus y to the 1/3 over 3x to the 2/3. All of that is being divided by x to the 2/3, because whenever you have a power to a power, you multiply powers. Now, I just want to simplify that a little bit. So I'm going to multiply by basically all of my denominators so that I can cancel them all out in one swoop. So I notice that I have a 3 in the denominator, a y to the 1/3 in the denominator, and an x to the 2/3. So I'm going to multiply by all of those things. I'm going to multiply by 3 y to the 1/3 x to the 2/3 to both the top and the bottom. 3 y to the 1/3 x to the 2/3. And I'm running out of room, so we're going to move this over here. Okay, when I multiply 3 y to the 1/3 x to the 2/3 to this first term, the 3's are going to cancel, as well as the y to the 1/3, leaving me with just x to the 2/3. So I will have x to the 2/3 left over from this term. Then when I distribute that term to this second part, the y to the 1/3 over 3x to the 2/3, the 3's are going to cancel and the x to the 2/3 are going to cancel, leaving me with y to the 1/3 times y to the 1/3. So I'll just write that like that for now, y to the 1/3 times y to the 1/3. All over, and then I basically just multiply all this stuff together. So I have a 3 y to the 1/3 x to the 2/3 times x to the 2/3. So then that simplifies down to x to the 2/3 plus y to the 2/3 all over 3 y to the 1/3 x to the 4/3, because when you're multiplying the same base, you add the powers. And these are both 2/3 power, so that adds up to 4/3 power. Okay, but you might think we're done, but we can actually simplify one more thing, and that has to do with this expression right here, x to the 2/3 plus y to the 2/3. I want you to look on this page and see if you see that expression anywhere else in this problem. So I'm hoping you located it. It's right up here. It turns out that x to the 2/3 plus y to the 2/3 is equal to 1. So that means right here, x to the 2/3 plus y to the 2/3 equals 1. And since it equals 1, I need to reduce it down to 1. So my final answer is 1 over 3y to the 1/3 x to the 4/3. And that's the final answer for the second derivative. The first derivative was right here, negative y to the 1/3 over x to the 1/3. The second derivative, after all of that work, reduced down to 1 over 3 y to the 1/3 x to the 4/3. So this example was probably one of the most complicated. They are not all going to be nearly this challenging. This one just was challenging because of all the fractional exponents. So there's a lot of algebra 2 that was going on here that you'd have to remember. Plus, we have to keep very careful track of each part of the derivative to avoid making mistakes. Also, another thing I want you to get from this example is sometimes, either when you're finding dy dx or when you're finding the second derivative, d2y over dx squared, you will have to substitute, like here, for example, with u prime, I had to take out dy dx and substitute it with what it equaled. And in the very end of the answer, I had to take out the x to the 2/3 plus y to the 2/3 and substitute that with 1, which came from the very beginning equation. That is a very common occurrence when you're finding a second derivative, is having to substitute out part of the answer for some previous information that was either found earlier or given earlier. So keep your eye out for those kind of substitutions when you're doing these derivatives. And that concludes our lesson on implicit differentiation.